In the first part of today's lectures, we are concerned with the membrane potential again. We will derive the Goldman equation that tells us the membrane potential from the concentrations of the ions in the cell. First, a recap of last week's lecture, where we looked into the Donen equilibrium. So we were concerned about the ion concentrations inside and outside of the cells, and we were wondering whether this membrane potential of minus 60 millivolt was determined by the Nernst potential. Well, because we are dealing here with multiple ions, we could assume that all ions are in equilibrium. That leads us to the Donen equilibrium, saying that the ratios of the inside and outside concentrations of the relative ions has to be constant. Yet that is not the case. And there are various membrane potentials for the various ions. Now, one way out, in order to further explain the situation, is that we actually look for a dynamic equilibrium, or a steady state, in which we also concern fluxes of ions and electrical fluxes through the membrane. For that, it was very handy to cook up an electrical equivalent circuit of the membrane as a series between a resistor and a voltage source. Now, considering that, we found that the membrane potential is in particular set by the potassium concentrations of the cell. Further, we found that the concentration of the potassium, likewise as for the sodium, are set by a membrane protein, which is the sodium-potassium pump, that highly regulates the concentrations of both sodium and potassium. So let's consider two compartments, an outside compartment and an inside compartment, characterized by the ion concentration of the outside and on the inside, separated by a thin membrane. The size of the membrane, typically from lipids, is typically 5 nanometer, and applied is a potential delta V. Now, because of this potential delta V, there will be some flux, ion flux, through the membrane. And this ion flux J we would now like to calculate. Now, for the particle flux, we assume the particle flux is given by two parts. The first is a diffusive part, hence the ion flux J is equal to minus d times the gradient in the concentration, plus an additional part that explains the drift due to a potential, to the potential drop, which is here summarized by d times the drift velocity times the concentration. Now, from non-equilibrium physics, or statistical physics too, we know that the drift velocity is given by two parameters. The first is the friction that represents how fast particles could move, zeta, and the applied force F. Now, for the friction, Einstein told us that the friction is connected to the diffusion constant, as the friction coefficient is equal to the diffusion constant divided by kBt, where the force is the electric force on a charge, hence is E times the delta V divided by d, so the electric field. Now, combining those, we obtain that the flux is equal to minus d times the gradient of the concentration minus E divided by kBt times delta V divided by d times the concentration. Now, this equation is the so-called Nernst-Planck equation. It is now obvious that if we solve the Nernst-Planck equation and solve for the concentration gradient, we know the flux. And since the Nernst-Planck equation connects the flux with the membrane potential, we obtain the membrane potential. Now, this is exactly the route that we will take. As a first step, it's useful to define a reduced membrane potential given by U is equal to the electric E divided by kBt times Z, the number of charges per ion, times delta V, which relates the electrical energy E times Z times delta V with the thermal energy kBt. Now, if we rewrite the Nernst-Planck equation in terms of U, we obtain that we can rewrite the Nernst-Planck equation as the gradient of C, dC by dx, is equal to U divided by D times the concentration minus J divided by D. Now, this equation we can rewrite in a form that dx is equal to dc times U divided by D times C minus J divided by D to the power minus 1, which we could integrate across the membrane. So the dx we will integrate from 0 to D, the thickness of the membrane, and the dc, the concentration, we will integrate from the concentration inside to the concentration outside. Now, doing so, we obtain the relation between the thickness of the membrane and by integrating 1 divided by a function, giving the log of the function at the two boundaries, and finally leading to an expression for the reduced potential of e to the power u is equal to U divided by D, C outside, minus JD divided by U divided by D, C inside, minus J divided by D. From which we can finally solve the particle flux as a function of this reduced potential, where J is equal to D divided by D times C inside e to the power U minus C0, C outside, divided by e to the power U minus 1 times U. So now we solved for the particle flux. So it's good to look on for special cases, and one of the special cases that there is no potential, hence U is equal to 0. In that case, the product of U divided by e to the power U minus 1 for U approaching 0 goes to 1. Hence, what we obtain is that the particle flux J is equal to the diffusion constant divided by the thickness times the concentration difference between the inside and the outside. Now, last week we considered also that the flux you also could express in terms of the permeability coefficient, PD, times the concentration difference between inside and outside. Hence, what we obtained here is a microscopic description of the permeability coefficient, giving that the permeability coefficient is equal to D divided by the thickness of the membrane. Hence, it's given by diffusion. Okay, so now we're ready to put everything together. We have to consider that the membrane is at steady state. Hence, the total flux of ions given by the flux of the potassium ions plus the flux of the sodium ions minus the flux of the chlorine ions, because they are differently charged, has to be 0. Otherwise, there would be a pileup of charges either on the outside or on the inside. Okay, so we have to add all those fluxes, and we obtain a somewhat lengthy expression where we use the particle flux that we just derived for the different ions. Now, in this equation, we interchange the diffusion constant divided by the thickness of the membrane with the respected permeability coefficients, P of the potassium ions, for the sodium ions, and for the chlorine ions. Now, what follows is that we assume that the membrane potential is significantly different to 1, so it's much larger than 1. Then factors like e to the power u minus 1 divided by e to the minus u minus 1 is about minus e to the minus u. So in that case, we can rewrite the above equations, obtaining a relation between the permeability coefficients and the relative concentrations of the ions with the membrane potential, or e to the power u of the membrane potential. Now, solving that for e to the power u, we obtain a simple relation relating the inside and outside concentrations as well as the permeabilities for the different ions. Now, solving for u and transferring back to the real membrane potential delta V, we find that delta V is equal to kBt divided by E times the log of the ratio P of the potassium ions times the concentration of potassium ions outside plus P of the sodium ions times the concentration of the sodium ions outside plus P of the chlorine ions times the chlorine concentration of the chlorine ions inside, divided by the reverse concentrations of the different ions. This is called the Goldman equation. Now, the strength of the Goldman equation is, and this detailed view is, that if we now plug in the numbers that we know for the respective permeabilities and also for the inside and outside concentrations of the ions, we obtain the realistic membrane potential of minus 60 millivolt.